Good afternoon. Welcome to the CERIAS Security Seminar at Purdue University. Today it's my great pleasure to introduce Professor Chen from University of California, Davis. Professor Chen is an assistant professor in the computer science department at UC Davis. He received his PhD in computer science from UC Berkeley in 2004. His research interest is in computer security with an emphasis on wireless security, web security, and software security. In 2007, Professor Chen received the NSF Korea Award to support his research in wireless security. Oops. Oh.
Thanks, Dongyan. Hi, everyone. Thanks for coming to my talk. So this talk describes a project that's supported by the NSF Career Award. So the goal of the project is to identify unique vulnerabilities in cellular data networks. So we have been looking at vulnerabilities on the internet for a decade, and we think that we know more or less the vulnerabilities there. But as computing moves to the cellular data networks, what new vulnerabilities are there, and how can we deal with these new vulnerabilities? This particular work focuses on the scheduling algorithm in the third generation cellular data networks. And this is a joint work with my student, Radmilo Rasic, and Dennis Ma and my colleague, Xin Liu at UC Davis. The third generation cellular data networks provide a high-speed downlink data access. For example, there are two example technologies. One is called HSDPA, high-speed downlink packet access. The other one is called EVDO, evolution data optimized. HSDPA is being deployed by some U.S. major wireless cellular carriers in major cities. In the San Francisco Bay Area, HSDPA is being deployed. The reason why they can offer high-speed downlink data access is that they exploit the multi-user diversity. So multi-user diversity means that your cell phone's channel condition varies, depends on its location and the time. Okay. There might be some interference such that suddenly your channel condition gets bad. And when you move to a bad area, such as inside an elevator or a corner, your channel condition might also get bad. However, chances are that at any given time, a subset of cellular devices have relatively good channel condition. And this is the basic intuition behind multi-user diversity. You might think that multi-user diversity is a bad thing because new cell phone can get a stable channel condition. But rather than fighting against it, people have tried to embrace multi-user diversity to improve the throughput of a cellular data system. And this is achieved by algorithms called opportunistic scheduling. So let me give you some brief background on multi-user diversity. So in a typical opportunistic scheduling algorithm, the base station uses time division multiple access to divide a channel into time slots. Okay, to chop the time into different slots. And each slot is about 2 milliseconds in HSDPA and 1.67 milliseconds in EVDO. This is called the transmission time interval. So the assumption behind opportunistic scheduling is that each cell phone's channel condition changes independently, okay, both in time and in location. However, at any given moment, some varying set of cell phones have relatively good channel conditions. Therefore, opportunistic scheduling tries to embrace this multi-user diversity by asking every cell phone to report its channel condition at every time slot. So once the base station receives the channel condition reports from all cell phones, the base station will pick a cell phone with a relatively good channel condition to be scheduled in the next time slot. Among all the algorithms for doing opportunistic scheduling, a very common algorithm is called the Proportional Fair algorithm. Once you do scheduling, you have to strike a balance between maximizing the system throughput and reducing the delay. Right? If you just want to maximize the system throughput, you always want to schedule the cell phone with the best channel quality. But if you always do that, then some cell phones with bad channel quality would starve could be forever. So you always want to strike a balance. And in particular, this proportional fair scheduler tries to strike a balance by maximizing the product of the throughput of all the users. Here is the particular scheme used by this scheduling algorithm. So the base station tries to maximize this value. The numerator of this value is the instantaneous channel quality of a particular cell phone user I. The denominator is the average throughput of the same user. As I just described, there are two values. One is the instantaneous channel quality. The other is the average throughput of the same user. And the average throughput of the user is calculated using a sliding window. Okay, this is your typical sliding window calculation. If the user I is scheduled at that time slot, then its average throughput is increased by the sliding window. If that user is not scheduled at that time slot, then its average throughput is decayed by a factor of 1 minus n alpha. Okay, so much for the background on proportional fair scheduler. So what vulnerabilities did we find? Well, we found two vulnerabilities. The first is that at each time slot, every cell phone reports its channel condition to the base station. But the base station does not verify the authenticity of the channel condition report. And in fact, it's very hard for the base station to verify the channel condition because one has to measure the channel condition at the location of the cell phone. Since the base station could be far away from the cell phone, it's not feasible for the base station to verify the channel condition reported by the cell phone, because the cell phone could be hiding behind a metal shield or inside an elevator, and there's no way that the base station can know that information. Another problem with proportional fair algorithm is that even though proportional fair guarantees fairness, the fairness is only guaranteed inside a cell. Once a cell phone moves to different cells, the fairness is no longer guaranteed. And I'll show you in a moment how this can be exploited by attackers. So one fundamental reason behind these vulnerabilities is that cellular networks were designed with the assumption that all the cellular phones are trusted. So this probably is an artifact carried over from the traditional landline telephone designs. In the traditional landline telephone systems, a telephone device is issued to you by your telephone company, and there's not much that the telephone can do besides dialing numbers. So